you can see a couple of nice images here. I'm just trying to show a couple of examples of how can we discover new molecules for grid level energy storage. I think the topic of my talk is energy storage. So first couple of slides, I would like to show the growing landscape of and some gaps in the energy storage. If you look at the left side, the energy storage came a long way, and if you look at around 2% of our personal electronics is a lithium-ion battery within the last 30 years, and also 28% of U.S. energy consumption is around transportation. And if you look at it, a very small amount of the transportation sector is electric. So one of the future needs are electrification of the transportation sector so that decarbonization is faster. I think this is a three-side problem. One is a modern world is looking for a decarbonization, slowly inching towards it, and the developing world is looking forward to the breakthroughs in better energy storage, both in personal vehicles as well as the grid storage. And on top of this, I think around 800 million people today don't have electricity or energy storage. So there is a huge opportunity space for making some revolutionary efforts in this energy landscape. And on the right-hand side, I listed few gaps in terms of energy storage. So we don't have a strong grid storage for many hours, many days. And also this energy, the technology at the moment is heavily dominated by lithium ion. The cost is already came 10 times lower in last 20 years. It's going to be very difficult to challenge the fossil fuel. So we probably have to replace some of the expensive metals like cobalt, nickel, those kind of things to earth abundant domestic supply chains. And also there may be an opportunity to completely change lithium to some other metals like sodium or magnesium, which are much more abundant than lithium. So on the last part, I think last couple of bullet points, this is much more dependence on large scale storage for buildings and large sectors. You need a grid type of storage. Probably we have to move away from lithium to some other technology. So on the left, you can see a figure from Argonne National Lab. We have identified the usable specific energy density of various energy systems. On the bottom left, you can see Nissan Leaf and Tesla models. They are around 100 to 200 specific watt-hour per kilogram usable scale. So if you, for example, if you want to fly a Boeing 777 or something like that, you probably need 800 or 900 watt-hour per kilogram. So that require we need to change the whole energy storage architecture. Like, for example, going away from simple lithium-ion intercalation batteries to something chemically storing, such as a lithium air system. There is energy stored in covalent bonds. So the application domains of this battery, you can see that when personal cars are really happening, long-haul trucks are a contender. I think there could be some other options other than typical batteries. You may be able to do hydrogen. It is rail, marine, and aviation. They are difficult, too large and heavy. So require some sort of a combination of techniques of batteries or chemical energies, such as hydrogen technologies. So the bottom one is grid storage. This is something we have to invest heavily on, so that we can utilize the energy from sun, energy from wind, etc. So at the moment, the lithium-ion battery technology is used in this grid, that they are only limited to 4 to 6 hours. So one of the concepts, so I'm going to explain some of the beyond lithium-ion concepts. For example, 4 examples I'm showing here. One left is a flow battery. Here we are looking at storing molecules in a tanks, and the molecules undergo oxidation and reduction, and the difference in free energy can be converted to electrical energy. So it is highly scalable because of the energy density is directly proportional to the tank size. So so it could be scalable. One of the bottleneck is identifying right molecule or right materials. They can flow and they can remain stable for a long period of time. So that's a challenge. The second example is lithium air batteries, where lithium and oxygen can come together and do reactions to make lithium oxides. So this is a chemical bond formed between lithium and oxygen. So it's a large amount of energy. So if we can do reversibly, this would revolutionize energy storage. A similar concept is similar concept exists in lithium sulfur technology. I think they already have some commercial lithium sulfur for drones, not commercial, at least just test system for drones. One another system is in early development is if you change lithium to multivalent materials such as magnesium or calcium or a zinc. So now we have multiple electrons we can access, so that the energy density can be improved significantly. So all of these are in very much into like fundamental research. I think the beauty of these systems is these are all require some a priori calculations, so that otherwise, it's going to be Edisonian approaches. So AI and simulations can play excellent role in all this research. So just one example. So during the last 10 years, we have looked at various molecules for the redox flow battery. So on the right-hand side, you can see a leaderboard molecules. There is many molecules, 10 or 15 molecules drawn there. So if you look at on the right-hand side, the molecule undergo oxidation, and the left-hand side, the molecule undergo reduction. So theoretically speaking, you can make a battery out of 2-volt catholyte and 2-volt anolyte that make a 4-volt battery from the organic molecules. So in terms of predicting what molecules to use next for this storage, it's a multi-objective problem, because of the molecule has to be reasonably stable. They have to exhibit redox behavior at given potentials, and also they should be less toxic and less soluble and more soluble. And also you can put a lot of co-design properties such as self-repairing ability or self-reporting ability, so that when they change the state of charge, it will show a different color, so that we know that the molecule undergo certain degradations. And also they have to be extremely stable. So this is one example I just want to show from our group. So we looked at this as a multi-objective scenario, multi-objective optimization scenario. So we have 2 publications. You can check it out. But the main message here is, if you have a very large chemical space, such as, let's give an example. We are looking at a molecule like a benzothiazole. We can synthetically make many type of these molecules from the large chemical space. So how can we come up with a molecule with a couple of desired properties? So in this publication, we picked 3 desired properties to answer a multi-objective scenario. 3 properties are reduction potentials, and solvation free energy, and lambda absorption, which is absorption, UV absorption wavelengths, which is directly connected to the fluorescence. That means the molecule will start showing fluorescent behavior upon the state of charge. So in the summary of this the project here, so we used the active learning approach. So here, so we started building a smaller data set of 1,400 molecules. Among that one, we know that around 22 materials are in the Pareto front of that based on these 3 properties. So we developed this multi-objective optimization based on Bayesian approaches. So if you look at the left side, you can see on the diagram, there is if you pick randomly from this 1,400 to get this 22 molecules, it's require around 1,000 experiment or 1,000 DFT simulations. But if you use a multi-objective optimization, you can get it this 22 molecule within 120 experiments or DFT simulations. So we expanded this to a 1 million data set. We created 1 million molecules of similar core structures, and we did this Bayesian type of approaches, and we came up with around 16 more new molecules within 100 evaluations. So I think this clearly shows a power of active learning, to come up with these molecules. Having said, this is all highly specific to this particular system, and I just want to point out one more thing. So this whole energy storage research is now really getting going. Having said that, if you have more data, you have more confidence in this data. So the molecular data sets, I'm just only showing a few examples. They are very limited. I mean, if you look at the molecular sets of redox flow batteries, it's 125,000 materials, and materials project is also relatively small compared to other data streams available. And the reactivity of these materials under these conditions also very less. So the whole point I'm trying to say is, like, we need a targeted high fidelity data generation effort. I think maybe national labs can lead some of these efforts. We need efforts in new electrolytes, new electrode materials, new membranes, and new condition optimization. I think that's all I have. I think these are the smart people really contributed to this work. Thank you.